Like you may not want to disclose that to everybody. Sorry about that. That's kind of asinine of me. Some of you already mentioned you wanting to retake test 2, but your next test is the first test with me, so hopefully, having to relearn a whole other teacher's, testing strategy isn't going to throw you for too much of a loop.
I don't know what's up, man. I had the gist of everything, but screwed up little bits and pieces here.
I know, and it was frustrating. There were some good grades. Don't get me wrong. Congratulations to those of you got a grade that you're happy with, and I know happy with is relative. So some people are happy with a 97. Some people are happy with a 78. So if you're happy and it, clap your hands for your grade. But any questions? If you don't want to ask in person, we can stay after class and I can go over some one-on-one questions with you. But the retest, the second attempt on test is again, it's available for test 1, 2, and 3. And probably the best time to do it would be after we have done test 3. So that way, somewhere between test 3 and test 4, you can figure out, okay, I want to focus on retaking test 2 or retaking test 1 or test 3, and then that'll, we'll do that in that couple of week period for the end of the semester, and then shift the focus to really doing well on test 4. Test 4 is most likely going to contain some open notebook elements to it. So you'd actually, because the last chapter is really kind of a note card worthy chunk of material that you kind of get at the end of the Calculus 3 semester. So I'm not going to be able to cover all of it that's usually covered, but what I do, I'll let you know what you can actually have access to on the test in terms of using a formula sheet or things like that. Jared.
I'm assuming if we choose to retake one of the tests and we happen to do worse on the retake, then we keep it better.
Yes, ideally you don't do worse on the retake, because what I'm going to do is I'm going to get the Word, I've already got her Word copy of test 2, I'm going to get her Word document copy of test 1, and then you'll see my test 3, and I'm just going to keep the same format. Like I'll probably turn this into a zekoid who's, I don't know, 8 meters to the right of the origin, and then his initial velocity is 4 meters per second upward, and then maybe change the acceleration, but it still has the same rudiments. Integrate acceleration to velocity, find out your c-values, integrate velocity to position, integrate, find your c-values and stuff like that. Okay. Any other questions?
Were you a bit more forgiving on this test because of this whole situation with changing teachers and everything? Like versus like partial credit?
Was I more forgiving, or?
I'm just wondering.
I didn't. I sort of a psychological subliminal thing. I didn't. I don't think I was intentionally softer on the grading. Or what do you feel you were unfairly assessed?
No, I thought everything was fine. I just was wondering how. If you were giving us a break.
No. Honestly, I probably did about 6 Jaeger shots. Then I started doing the grading, and everything was fine. And if that's deleterious to your grade, I'll make sure I grade the next one sober. I'm just kidding. I'm just kidding about the Jaeger shots. Please trust me. Especially with no Dr. Pepper chaser. Oh, God, you got that on video, crap. Jacob? Yeah. So you're Jacob. All right. Thank you, sir. If y'all have any one-on-one questions about the test, specific problems, or just any kind of question in general that you don't feel like asking in the public forum, feel free to stay after class tonight, just, for whatever you want to ask, and we'll try to get some kind of privacy if you don't want anybody around when you ask that question. So the key will be scanned in, and I need to do the same thing with test 1. As soon as I get her copy of test 1, I'll make a key out for it and scan it in, so that way when you do your retest, you can look back over the format of the original, so you can kind of see, where your weak spots were, what you need to iron up, and really be solid on when you take your second attempt. Okay. All right. Any homework questions? Problems from gradient, directional derivatives, chain rule, d-test? Maybe if you've cracked into double integrals.
Were there supplements for the gradient and stuff we did earlier, like there are on these?
I went ahead and put up I think I did put the homework supplement for gradient. I do not have one for chain rule, so your chain rule experience needs to come from the textbook. But I've got supplemental stuff for gradient and directional derivatives for, not for chain rule. And then we went into double integrals. I've got a supplement for that. And then it's a long one. It's 28 problems because it technically covers What I know, right? It covers what would be on 15.1 and 15.2 all together. And then triple integrals has one. But one thing I've discovered in looking over the notes for triple integrals, there's one particular problem in the notes that's going to require us to know polar coordinates before we get there. So if you look at the outline of test 3 topics that I've got on D2L currently, it's the gradient directional derivative stuff first, and then it's got the chain rule stuff, and then it starts the double integrals that we started this past Thursday, and then it goes into triple integrals. So what I'm going to have to wedge right here between double integrals and triple integrals is double integrals in polar coordinates. So currently, I like to just go ahead and add that as a test 2 topic. So that way test 2 covers gradient, directional derivatives, chain rule, double integrals over rectangles, and double integrals for tonight, what we talked about for, like function-based regions, polar coordinates as double integrals, and then triple integrals in XYZ coordinates. And I'll make the final call on Thursday just because I'll obviously be making the test out between Thursday and Saturday. Well, and the time window for the test would be Saturday, this coming Saturday. I'll put it in the testing center. Anybody would be interested in taking test 3 on Saturday? Okay, all right. So it's going to be open from Saturday, and then it'll be available Monday, Tuesday, and Wednesday of next week. So if you want to do it Saturday, I'll double check again on Thursday. I can put it in there on Saturday at the earliest. If nobody wants to take it, that'll give me till Monday to toy around with making the test. But no, I can get it made out by Saturday if someone wants to take it. And then you have that 4-day window, Saturday, Monday, Tuesday, Wednesday of next week to do that. Okay? All right.
So if you don't get it until Monday, we have till Thursday to take, right?
Pardon?
If you don't get, you said that if nobody takes it on Saturday, then you can postpone it till Monday.
No, you can still take it Wednesday. Oh, you can take it the following Monday, but those will be the days that it's available, Saturday, Monday, Tuesday, Wednesday. So that way, if we wrap up everything on Thursday night, and you still want a contact hour before you commit to taking the test, really that narrows it down to Wednesday. That sucks. If you wanted to wait till Thursday to get the following Tuesday to get some questions answered. So I think that's pretty reasonable, I think.
Saturday, Monday, Tuesday?
So Saturday, Monday, Tuesday, Wednesday.
Oh, Wednesday.
Yeah, so it'll be in there for 4 days. And Tuesday and Wednesday are the most robust days available, but I imagine there's a handful of you who have Wednesday night classes too. Sorry. So, again, we'll talk more about that on Thursday. Any other questions? Any what ifs? What the heck's? Where the heck? Why the heck? Yes.
It looked like for the supplemental homework on gradient and directional derivatives, I only saw the key for number 1 and 2.
Oh, let me look that up after class. Let me double check because I haven't signed on yet, and it's going to take a while for this thing to boot up. Let's boot it up. So you only see the answers to the first 2 problems.
I think so, yeah. I didn't print it off, but
No, they're all there.
okay. I
Oh,
probably
they're there?
wasn't looking the right place
Yeah.
then.
Okay.
I figured I wasn't looking the right.
Maybe whenever you're loading a PDF on D2L, it could be that it takes a little while to load the subsequent pages. So maybe if you just saw the first page, you just give it a second, because my browser's the same way at home. It takes a while to load all the other maybe 2 or 3 pages of the PDF.
Okay.
So you've got them though? You've got that?
Yeah, it went 1, 2, 3, 6. So it skipped 4 and 5.
Yeah, so
Okay, so there are a couple missing. So yeah, they're missing. I'll just need to write those up and give them to you. Yeah. Did you want to see those? One of those worked out just to see if you got your answers right, or? Okay. Got the D-test. Here's double integrals. There's triple integrals. There's polar integrals. Ah, of course. You're gonna have to sign on anyway. So that'll take it a second to do that. Do you have the gradient problem set? And so it's numbers 4 and 5 that are missing, solutions to 4 and 5. So on number 4, it's a function of 3 variables. So you're wanting to take this function of 3 variables, evaluate its, or find its gradient first, evaluate the gradient at the point P. So again, since that's a 3-dimensional function, or a 3-variable function, I'll need a 3-dimensional point to plug into it. And then, what is the directional derivative of the function f at the point P in the direction of a unit vector u? So you got that circle, because that's one tiny detail you got to be careful of. Sometimes you're literally given a unit vector. In this case, on the 4, you'd have to actually unitize that vector to turn it into the vector u to use your directional derivative. So on number 4, is natural log of 3x plus 6y plus 9z. So part A, the gradient of this function will have 3 components because you've got 3 independent variables. You'll have a partial with respect to x as your I component, a partial with respect to y as your j, and a partial with respect to z as your k component. So when I build those all together for this function, the partial of this with respect to x, the natural log is the outer function, so that makes you do 1 over, the 3x plus 6y plus 9z. The chain rule makes you multiply this by the inner derivative with respect to x. So the y and the z terms would vanish to 0. So technically that puts a 3 in the numerator of that fraction. Your partial with respect to y, is that okay? 1 over from the ln, and the chain rule multiplies by the inner derivative, which will multiply 3 in the numerator. The partial with y would look similar. Your ln is still the outer function, so you still have this denominator that looks exactly the same. But now your partial with respect to y puts a 6 up top. And when you build your z partial, same denominator, partial with respect to the inside on z gives you a 9 in the numerator. So that's the answer to A. It's just what is the gradient of the function. It looks something like this. Okay. And then part B, it says to evaluate the gradient at the point. Well, the point given is 1, 1, 1 for x, y, and z. So you just carefully go through each component and plug in 1 for, well, for everything. That's going to give you 3 divided by, let's see, that's 18. So 3/18 is usually 1/6. 6/18 is 1/3, and 9/18 is 1/2. So that should be the gradient evaluated for 1 being x, y, and z. So that's just like function input and output. Just make sure you go in x, y, z order, just in case each of the 3 coordinates are unique. Like 1, 2, 3. Just match them up very carefully when you plug them in. And then part C, you want the directional derivative of this function at that point in the direction of a unit vector. So you have to take this vector v and unitize it, which means divide it by its magnitude, and that would guarantee to turn that v into a unit vector. So the vector v given in the problem is -4i, 12j, and 6k. And actually, you can make this easier.
Factor out 3.
Well, actually, divide out a 4. So it's not really the same as v anymore, but if I divide out a 4, do you see the convenience of doing that? First off is, do you see why? I just want to make my magnitude easier to deal with. 6 divided by, 6 doesn't divide by 4. Well, you can divide it out by 2.
Yeah.
So 2, it's early in the evening, sorry folks. The arithmetic sucks at first. So the components become -2, +6, and 3, okay? And the only reason I'm doing that is just to make my magnitude simpler to deal with. I'm taking the square root of a smaller number when I just divide that out. But is this still guaranteed to be parallel to v?
Yeah.
Yeah, I just divided by a scalar of 4, so it's still parallel to it. Is it a unit vector yet? No. So I still want to find its magnitude. So that's the square root of 4 plus 36 plus 9. So, well, that works out nicely. Your magnitude is 7, because that turns out to be 49, and I believe the square root of 49 is still 7. So that means our unit vector u is going to come from these components all divided by 7, and that'll shrink the magnitude of the whole vector down to a unit length. Negative 2/7 for I, 6/7 for j, and 3/7 for k. So what two things on this page do we need to calculate that directional derivative?
U and the delta, or the partial derivative?
And well, not just the answer to A, actually the answer to B, because we want a constant vector for our gradient dotted with a constant unit vector, because you'll get a scalar as your answer for a dot product. And it's really long wording. You're prompted for the directional derivative of f at p in the direction of u. So, we took the gradient of f up here, we evaluated at the point P here, so we need that as one of our parts of the gradient, or the directional derivative. And then this is the unit vector that's imposing our direction that we're heading toward. So that equals the gradient dotted with the unit vector. And that's why you should anticipate a scalar answer. So that will dot our 1/6 I, 1/3 j, 1/2 k from the answer to part B with negative 2/7 I, 6/7 j, and 3/7 k. And this gives us, let's see, negative 1, that's going to cancel with 3, so 20 plus, 3 goes in there 2 times, so plus 2/7, and then plus, cancel them there, 3/14. So that's going to equal 21/42. That's going to make negative 2, that's going to make 12, and that's 6 times 2, yeah, usually 12. And then 14 times 3, so plus 9. So you got 19/42. Do you believe that's irreducible? Sarah, do you remember if that's what you happen to give? If
I had one math error. I ended up with a 3 instead of 1/6, so
Oh.
I have no answer.
Did anybody check this one out and happen to get 19/42? Because I've got this, I have to have the solution written somewhere, because I've got the solution keys to all these written up on my H drive. But apparently the ones I posted online skip the answer to number 4 and skip the answer to number 5. So I knew I got it somewhere. I bet if I just go to, let me look up something real quick. I'm going to go to the last time I taught this class, spring of last year, and see if I actually have the gradient calculated there correctly.
Yeah, I come up with the same thing once I fix that.
Okay, so that's at least one validation. Oh, here we go. Alright, so let me talk my screen out. Yeah, back in, apparently I did the same thing spring of last year, because the solution to numbers 4 and 5 on the gradient supplement was left off there, so that prompted me to make this little extra link on their it was their test 2 material. So I'll just go ahead and steal this from this page and post it on your page so you can have 4 and 5. Or just double check right now. The answer to number 4 should be 19/42, so I did it right. And then the answer to number 5, if you want to double check it, it's a funky answer. Turns out to be 22/√30 apparently, so it's a real number, it's a positive number, it represents a slope. Just, funky little irrational number. So yeah, apparently the same thing happened there, so that's what prompted me to do this. So I'll double check exactly what other documents are on their page that need to be on your page accompanying this material. So, and please let me know, either email or bring it up in class if you find mistakes, or if you find something missing, or some kind of link is funky and not working on D2L. Hopefully there's something I can do to fix it. Yes, sir.
Just go back up to 4.
Yeah. So apparently, when I worked this one out, I went ahead and found the magnitude of b itself. And that makes sense. We divided out of 2 to make the number smaller. We got a magnitude of 7. If we left the 2 in there, the magnitude should be twice as long. So the magnitude there is 14, but it still guarantees the same unit vector, because everything's going to be parallel. When you scale it down, that's the only unit vector you can get. And then knock those two together, 19 over 42 is your directional derivative. Any other questions?
And that's the slope of the gradient at the top.
Yeah, you have to kind of use the word slope in italics and quotes, because this is a 3-variable function, which means it's hard to see. A function of 2 variables has a 2-dimensional domain, like a plane, and so its outputs would be in 3-dimensional space. This is a function of 3 variables, which means its domain is a 3-dimensional space, and its outputs go into a 4th-dimensional, whatever that looks like, okay? So yeah, if you're, whatever it means to be standing on that function over its domain point 1, 1, 1 for x, y, z, and if you're looking in the direction of the gradient, that direction is the steepest direction you can climb from that point. But if you altered your direction into the direction of this vector, or its unit vector version, you'll be going at that slope. So if I take the magnitude of this vector here, should it be greater or lesser than that? 19 over 42. Should the magnitude of the gradient vector there be greater or lesser than 19 over 42?
Greater,
Why?
because it's not a unit vector.
No? Because the gradient points in what direction?
Steep.
The steepest rate of change, or the steepest climb. So if of all the places I can move from this surface at that point, that direction of that vector, I know it's in 3 space, but that direction of climb is guaranteed to be the steepest rate of change. Any alteration of that course by any other vector is going to guarantee a shallower slope. So if we take the magnitude of the gradient, which is 1/36 plus 1/9 plus 1/4, and then so the magnitude of the gradient would technically be about 0.62. 0.62 compared to this, well, that's less than 1/2. So 19 divided by 42, that's a slope of about 0.45. So the gradient, the steepest rate of change is the magnitude of the gradient vector. Any directional derivative you alter by any other unit vector's direction is going to guarantee to be a smaller slope, a shallower slope. Okay. Any other questions? And that one's hard to see. I can't draw a picture for this one because its domain is 3 space, but its range is 4 space. So the best we could do is just say, well, for an output of 1, you get this shape. For an output of 2, you get this shape. For an output of 3, you get this shape. And do level surfaces as opposed to level curves. So the topographic map here would be a set of probably concentric surfaces. It looks kind of weird. Hard to draw that. I'm going to sally forth, tally-ho, into double intervals, shall we? Okay. So, your turn, your homework too. I've got a copy of every other set of homework except for that one, the one that you prompted me for a question on. So, I need to keep on task with my own stuff. So, where we left off was I hit the pause button right here last Thursday night. Oh, sorry. I had stopped right here with this example, where this was the last example of doing a double integral over a rectangle. So when you're dealing with double integrals, the first ones you always see is when you integrate over constant regions for your x and your y. 0 to 1 for x and 0 to √3 for y here. But we're venturing into double integrals on regions bounded by functions as opposed to bounded by this to this for x and this to this for y, a rectangular region in the xy plane. So if your region is a little more organic and you're not integrating necessarily over a rectangle, what comes in handy is to be able to actually graph the underlying region that you're integrating over. Okay, so on this case, notice instead of constant limits for your x and y, the inner integral is beginning at y equals x squared and stopping at y equals 2x. And the x direction goes from 0 to 2. So one thing that's very paramountly important with double integrals is if you see variables on a double integral for its limits, the variables can only be on the inner integral. You can never see the variables in the outer integral. So the outer integral is always going to have constant limits of integration. The inner integral, or I need to go ahead and start speaking in plural, the inner integrals, because we'll get to triple integrals as well, where you have to integrate x, y, z order. The ones that are nested on the inside, those are the only ones that can contain variables on their limits, okay? So whenever you're breaking this down to see what the underlying region R is, the domain of this double integral is, what you want to do is go from the inside out. Okay, the inner integral is dy, the outer integral is dx. So what I usually do is, since you want to go from inside out, you want to pair y with this, x with this. Go ahead and realize that represents two y values. It's not two constant y values, but it's beginning at the y value where y equals x squared. So instead of y equaling 2, which would be a horizontal line, you're now dealing with y equals x squared, which is a parabola. So whenever I try to envision this shape, that lower limit tells me where y begins, in the y direction. So when I'm integrating y, the lower limit is y equals x squared, and then you integrate to the upper limit, which is y equals 2x. So that's just those two boundaries right there are going to guarantee you're not dealing with a rectangle, okay? And what I recommend, if you have to graph, and in some cases you do want to graph the underlying region, go ahead and graph these two on the same makeshift coordinate grid somewhere down here so you can see what the shape looks like. So if I graph y equals x squared is one of your pre-calculus favorites. Just that parabola vertex at the origin opening upward. Looks something like this, roughly. And then the other curve mentioned is y equals 2x. That's linear, slope of 2, y-intercept of 0. So it intersects at the origin. And the slope of 2 would look something roughly like this, about. Okay, let me extend this a little further down. Now, this would say y equals 2x down there. What you're used to, what you're accustomed to with integration is the lower limit's always less than the upper limit. You should try to impose that frame reference here, that sort of, the lower limit's below, the upper limit's above. Because when you graph both of these, is it entirely true that the parabola is below the line everywhere? Is there a place where the parabola's graph is below the line? Yes. Most likely, almost 99% certain, that's going to be the region of integration for this double integral. The place where y equals x squared, the lower limit, is below, right there, and y equals 2x, the line, is the upper limit up above. So there's only one snippet on the overlap of these two graphs where the parabola is lower and the line is upper. So most likely it's right there. What you want to do is cross-reference this with x's limits. X's limits, the lower limit for x is x equals 0. The upper limit for x is x equals 2. And keep in mind, this is two-dimensional. So what this means is if I'm looking at the graph of this region R, if I go in the y direction, and first off, take your index finger, and just let me know what you believe the y direction is. That's it. Going straight up, okay? Now, what is the x direction from where you're sitting? Yeah, I'm always talking about the increasing y direction than the increasing x direction, okay? So, and if I go in the increasing y direction, the first thing I hit is the boundary y equals x squared. That only happens right there. When I go in the increasing y direction, the only place I first hit y equals x squared is right there where it's on the bottom. And the same idea, the last thing I need to hit in this region is y equals 2x. The line has to be on the top. So that's guaranteed to be true right there. The first thing I hit in the y direction is y equals x squared. The last thing I hit is y equals 2x. And then that leaves the region. Now, do you know what these points of intersection are?
0 and 2.
Yeah, just happen to be the same values as our x limits on the integral. So if my y direction goes from the parabola to the line, and then x is bounded from 0 to 2, it happens to correspond to the points of intersection of those two graphs. The graphs do intersect at the origin, and right here on the parabola that will be the point 2, 4 because y equals x squared. On the line that will be the point 2, 4 because y equals 2x. So both points are guaranteed to be on the parabola and the line. They're intersection points. So this turns out to be our region R that we're integrating over, this tiny little sliver. Okay? And that's what our double integrals domains are going to start looking like. They're bounded by functions as opposed to being bounded by rectangles. Rectangles are obviously always going to be easier to work with, but occasionally you have some functional boundaries for your domain of the double integral, so it takes a little more attention. And then you're asked to evaluate the integral. Evaluation is no different. Evaluation still works the same way. You still go from inside out. So if I integrate x squared to 2x, x cubed plus 4y, my first order of integration is dy. So remind me how to do that.
You integrate with respect to y
And treat
X is gone.
and treat x as a constant.
any and all uses of x as a constant. So y is my integration variable. I'm going to focus my u substitutions, my antiderivative rules, my integration by parts, heaven forbid, but if I have to do it, it's all on y right now. Every use of x is constant. So the antiderivative of constant would be constant times y. So that goes to x cubed times y. The 4y antiderivative would be a proper 2y squared, because you need to do the power rule there. So the antiderivative process is still the same. One variable is treated constant, the other is your focus variable based on what the differential is, going inside out. Now remember, you're not plugging in numbers, you're plugging in variable expressions of x for the variable you just integrated, the y. So replace all these y's first with a 2x, because now you're doing the fundamental theorem. The upper limit gets plugged in for y, and then you subtract what you get when you plug in the lower limit for y. So carefully do that. Really, meticulous stuff you got to be careful with. So everything gets replaced for y, x cubed times 2x plus 2 times 2x quantity squared. That's what I should get when I plug in my top limit. Then my bottom limit's x squared, plugging that in for y. So x cubed times x squared, and then plus 2. Now y is being squared here, so that means x squared gets squared again when you properly evaluate that. So just be careful about your order of operations and making sure you're making your substitutions correctly. So I plugged 2x in there the right way. Let me put my parentheses there so you can see what y got replaced with. Both y uses got replaced with 2x here. Both y uses got replaced with x squared there. And just be careful with your algebra. You definitely want to finesse this and simplify it before you go to doing your outer integral, just, to make it a little bit neater and easier to deal with. Because some of these may be like terms in the mix. This is 2x to the fourth